Welcome to this video on enthalpy of phase change. We've taken a look before at how we change states of matter between liquid, gas, and solid, and today we're going to take a look at how the energy associated with those occurs, and specifically between the solid and the liquid phase, and then between the liquid and the gas phase. We're going to kind of ignore a little bit of that sublimation deposition. Grab your Cornell notes and let's get started. So our first question is, what are molar heats of physical processes? And we're going to not only have these phase changes, but one extra physical process. And so these molar heats, and remember heat is also called enthalpy, are the amounts of energy or the amount of energy for 1 mole of a substance to change. So they're changing either their phase change or their solution formation. Some sort of physical change is occurring. And we have 5 molar heats that we're going to take a look at for physical processes. The first one is heat of fusion, which is associated with melting of a solid. The second is heat of solidification, which is the process of freezing from liquid to the solid phase. Heat of vaporization, so going between liquid and a gas. And then for heat of condensation, going from the gas back into the liquid. And so those are all with phase changes. And the last one is what happens as we make a solution. So as we dissolve a solute in a solvent, particularly we look at aqueous solutions, what is happening with the heat or the enthalpy that's involved in that. Okay, so the first thing I want to do is kind of come back to this diagram that we've seen before. And we don't need to worry about the going between the gas and the solid, so I'm going to cover up those ones. But we are going to worry about these other 4. We just mentioned them. And so with these, we want to find out what's going on with the heats for these. And so I'm going to add a couple things into this diagram. And one of the things is that we see energy increases with the things that are red. So increase in energy and molecular motion, which means everything that's red is going to have a positive delta H. Okay, we're increasing energy, which means we are adding energy. And when we add energy, this is going to be, remember, an endothermic. Endothermic process. On the other hand, with the blue side over here, we are decreasing in energy, and so these are going to be a negative delta H. They are exothermic processes. And they are going to be releasing energy, and I think this is a little bit different from how we normally think of these, releasing energy or heat, okay, thermal energy. And so that's what we're going to see going on. And so we're going to see this one is going to be a negative, this one's a negative delta H, okay, for freezing and condensation. And then the other 2 are going to be our positive delta H's. Okay, so this one, I don't think you'll be able to see that. So positive delta H and a positive delta H. There we go. So that is something to keep in mind. What is going on? Endothermic, exothermic. Some of you have taken some additional biology before, and you'll see endergonic or exergonic processes. So be thinking about the energy involved with those. So that's a familiar chart that we've seen before, and the next one is going to be something new. And so you have this diagram actually on your notes already. And we want to know, how do heating curves represent enthalpy of phase change or heats of phase change? And so there's some really important things we're going to see here, and we're going to take a look. Let me see if I can find, I'm going to do my very thin line, see if that'll work well. Okay. So with this, we see temperature over here, and so this would be either degrees Celsius or it would be Kelvin. And we see heat energy, so this is going to be, so most of the time we look at this in degrees Celsius. Okay, and down here, this is going to be either kilojoules or joules. Okay, could be either. And we see some different things going on. And so one thing that we see is that temperature is actually increasing along the lines where we see that this is a solid, okay? So this is the solid line. We're going to see that there is a liquid line that's coming right up here. So this is where the liquid occurs, okay? And then finally we have our gas up here. Okay, and so as we see each one of these phases, we see that the phases themselves can actually change in temperature. So we see an increase in temperature along each one of those. However, we see a couple of different flatline areas, and so the flatline areas fall in right here. And so these two areas right here, these are where phase changes are occurring. Okay, so the green is where we see a phase change. And when we get to those points, we do not see that temperature is going to change. We see that there's going to be a process occurring here. And the amount of energy associated with this, so if I was to take a look, there is an amount of energy that occurs right here. If we're moving in this direction, this is actually the positive direction, so our final is going to be greater than our initial. And this one right here for melting is going to be a positive delta H, and this is what we call delta H of fusion, okay? On the backwards one, we're going to see this one is the delta H for solidification. So SOLID is how we're going to represent that. And this one actually happens to be negative. So this is the positive going this way, and freezing is the negative going the other direction. We see the same thing over here. This says boils. We actually want to have the word evaporation. Okay, boiling is the process, evaporation is where we're changing that state. And so this one is going to be positive delta H because it's going in this direction and increasing energy. And that is the enthalpy, or the heat of vaporization, so VAP. And going backwards over here, we see that this is the negative delta H then, because it's decreasing energy. And that is for condensation, so COND. Okay? And those are really the four that we're interested in. Now, if you've noticed, the amount for condensation and evaporation is the same amount of energy, okay? It's just that they're in the opposite direction, and the same thing down here. So the amount for fusion and for freezing is the same value, just in opposite directions. And so what we can do is we can say, well, we have delta H of fusion is equal to the negative delta H for solidification. And we also see that delta H of vaporization is equal to the negative delta H of condensation. Okay. Interestingly, these ones that are positive, I didn't write the positive there, but we could. These ones are going to be our endothermic. Okay, and these ones over here are going to be our exothermic. Okay, so that's just something to kind of keep in mind, because those are questions I like to ask and things that I want you to know about there. All right, so that is our heating curve for water. Let's take a look at some of these values that we can actually see for those delta H values. And again, because fusion and solidification are the same value, we just represent fusion, and then we would use the negative value of that for solidification. The same thing with vaporization and condensation. And what you'll actually notice is to go between the liquid and the gas state actually has a higher amount of energy. If you remember back to when we were talking about intermolecular forces, a lot of times those intermolecular forces in the liquid state happen to be pretty important things for overcoming these energies. And so we see a variety. You might want to write this down. These are in your book as well, and you can use the table in your book for doing some of your practice problems. Let's try a couple example problems with these. So the first one here, how much heat is required to melt 100 grams of ice? So how to calculate energy of phase change. This is what we'll do for practice. So the big question is, okay, this is for melting, okay, to melt ice. And if you remember, melting is fusion. And so we want to use this number right here. So melting is fusion. Okay. And so this is the value that we're going to use. Now we are in grams, and you see that this conversion is in kilojoules per mole. So the first thing we have to do is figure out our molar mass of water. Okay, so molar mass of H2O, and if you remember before, there's two H's, one each, plus 16 for oxygen, so we get 18 grams per mole. Okay. So what we want to do is we want to set this up. We're going to start with our 100 grams of water. Okay. Our first conversion, we want to go from grams into moles, so I'm going to use 18 grams on the bottom for every 1 mole of water. And then the second thing is that we want to use this value here. Now, since fusion is melting, we're going to use the positive value of this. Okay, so for every 1 mole of water or of ice, to melt it, it's going to be 6.01 kilojoules. So moles cancels moles, grams cancel grams, and when I multiply across the top and divide by the bottom number here, I end up getting a positive value of 33.39. We started with 4 sig figs up here, so I'm going to end with 4 sig figs, and our value is in units of kilojoules. Okay? So that's what we needed to do. And because we're melting ice, this is endothermic. All right, let's try one more example. So again, we're still calculating that energy of phase change, or enthalpy. And so in this one, it says how much heat is required when 100 grams of water vapor condenses. Okay, so our process here is water vapor is condensing. So the value has to be similar to that of vaporization, but it's going to be the opposite, since the delta H of vaporization is equal to the negative delta H of condensation. Okay, so we're going to have to actually take the negative value of this one. Again, we're going to use the molar mass of 18 grams per mole for water. So we're going to start off with our 100 grams. Okay, we need to change into moles, so for every 18 grams, there's 1 mole of water. And now for every 1 mole, because of this here, we are condensing, we need to make that a negative 40.7 kilojoules. It's a decimal there. Okay, we do the math on that, cancel our units. 100 times negative 40.7 divided by 18, and we get negative 226.1 kilojoules. Okay. This process has a negative value, so it is exothermic. Actually, condensing water ends up giving off some heat. All right. So the very last thing that we want to cover is the fact that we have some heats of solution. So what are these heats of solution? Well, the molar heat or enthalpy of solution is the energy absorbed or released when a solution forms. Now, we can't predict which way it's going to go with these. It really depends upon the solvent that's being dissolved, and we have to test this in a laboratory and come up with some standards. But here's a couple examples that we see. An exothermic process, one of them is putting sodium hydroxide in with water, and it will release some energy, and so this is exothermic here. It has a negative 44.5 kilojoules per mole. Endothermic, ammonium nitrate, if you put that in water and you mix it up in a solution, it actually has a positive value for kilojoules per mole. And so we see these in different things. Anytime you would make a solution and it becomes a little cooler, then that's going to be endothermic, and every time that it gives off some heat and you can feel it warm up is going to be warmer. And so that's really all that we need to know about the enthalpies of physical processes.